Welcome to SS2 Chemistry, Term 2, Week 3. Chemical bonding determines the structure and properties of all compounds. You have already studied ionic and covalent bonding in earlier classes. In this lesson, we focus on two additional bonding types, coordinate, dative, covalent bonding and metallic bonding, and explore how bond type determines properties. By the end of this lesson, you will define coordinate covalent bonding, explain metallic bonding using the sea of electrons model, relate bond type to physical properties, and apply this knowledge to WAEC questions. Let us begin. Ionic bonding, electrons are transferred from a metal to a nonmetal. The metal loses electrons to form a cation, the nonmetal gains electrons to form an anion. Electrostatic attraction between oppositely charged ions forms the ionic bond. Properties of ionic compounds: high melting and boiling points, strong electrostatic forces, conduct electricity when molten or dissolved in water, free ions, brittle, like layers shift, like ions repel, soluble in polar solvents like water. Example: NaCl, No. 281, loses 1E to Cl, 287, to give No+, 28, and Cl-288. Covalent bonding, electrons are shared between nonmetal atoms. Each atom contributes one or more electrons to the shared pair. Properties: lower melting/boiling points than ionic, generally, poor electrical conductivity, no free ions or electrons, except graphite, which is an exception, delocalized electrons, may be soluble in nonpolar solvents. Simple molecules: H2, O2, H2O, CO2, CH4. Giant covalent structures: diamond, tetrahedral C, hardest natural substance, 3D network of covalent bonds, very high MP 3547 degrees Celsius, graphite, layered structure, each C bonds to three others leaving one delocalized electron, conducts electricity, used in electrodes and as a lubricant, SiO2, silicon dioxide, constituent of quartz and sand. A coordinate bond, or also called dative covalent bond, is a type of covalent bond in which both electrons in the shared pair come from the same atom, called the donor atom. The donor atom has a lone pair, a pair of non-bonding electrons, that it donates to an acceptor atom or ion that has an empty orbital. The coordinate bond is identical to an ordinary covalent bond once formed, the distinction is only in how it was formed. Representation: drawn as an arrow from donor to acceptor, unlike the simple line for ordinary covalent bonds. Examples: ammonium ion, NH4 plus ammonia, NH3, has a lone pair on nitrogen, a proton H+, which has an empty 1s orbital, accepts the lone pair from nitrogen. The NH coordinate bond forms the ammonium ion. In NH4+, all four NH bonds are equivalent. The coordinate bond cannot be distinguished from the three ordinary covalent bonds. Hydronium ion, H3O+, water has two lone pairs on oxygen. A proton accepts one lone pair to form H3O+. The OH coordinate bond is indistinguishable from the other OH bonds. Aluminium chloride dimer, Al2Cl6. Aluminium is electron deficient, only 6 electrons in outer shell after forming AlCl3. A lone pair from chlorine of one AlCl3 molecule donates to the aluminium of the other AlCl3, forms a coordinate bond creating the dimer. This is why AlCl3 exists as a dimer Al2Cl6. Carbon monoxide, CO, has a triple bond, one of which is a coordinate bond, one lone pair donated from oxygen's lone pair to carbon's empty p orbital, represented as C, is identical to with a coordinate component. Nitric acid, HNO3. The NO bond to the OH group is ordinary covalent. The NO double bond involves one ordinary covalent and one coordinate, dative, component from nitrogen to oxygen. Metallic bonding is the electrostatic attraction between positively charged metal ions, cations, and a delocalized sea of electrons. In a metallic solid, metal atoms lose their outer, valence, electrons. These electrons become free to move throughout the metallic lattice. They are delocalized. The remaining metal ions, cations, are arranged in a close-packed lattice. The mobile electrons hold the positive ions together by electrostatic attraction. This is the sea of electrons model or free electron model. Properties of metals explained by metallic bonding: high electrical conductivity. Delocalized electrons move freely through the lattice under an electric potential. Metals are excellent conductors of electricity. Copper is the most widely used electrical conductor in Nigeria's power cables and domestic wiring. High thermal conductivity. Delocalized electrons can transfer kinetic energy, heat, rapidly through the lattice. Malleability and ductility. Metal ions can slide past each other without breaking bonds. The sea of electrons adjusts to the new positions. Metals can be hammered into sheets, malleability, or drawn into wires, ductility. This is why gold leaf can be beaten to 100 nanometers thickness and copper wire can be drawn into fine cable. High melting and boiling points. Strong metallic bonding requires significant energy to overcome. Most metals have high melting points. Iron MP 1538 degrees Celsius, copper 1085 degrees Celsius, tungsten 3422 degrees Celsius, highest of all metals, used in light bulb filaments. Exception: mercury Hg is a liquid at room temperature, MP-39 degrees Celsius, because its Si excess electrons penetrate the nucleus through relativistic effects, reducing metallic bonding strength. Luster, shininess. Delocalized electrons absorb light and re-emit it, giving metals their characteristic shine. The relationship between bonding type and properties determines the uses of materials. Ionic compounds, NaCl, MgO, CaCO3 used as table salt, NaCl, seasoning and food preservation, calcium oxide, CaO, cement industry, Dangote Cement Nigeria, fertilizers, ammonium nitrate, ammonium phosphate. Covalent giant structures, diamond, graphite, silicon diamond, cutting tools, drill bits for oil wells in Nigeria, graphite, electrodes in electrolysis of aluminium, aluminium production from bauxite, important since Nigeria imports most of its aluminium, silicon, semiconductors for electronics. Metallic materials, iron, steel, copper, aluminium iron/steel, construction, reinforced concrete, structural steel, bridges, vehicles, copper, electrical wiring, plumbing, telecommunications cables, aluminium, aircraft bodies, beverage cans, overhead power lines, lighter than copper for long-distance transmission, gold, jewelry, electronics contacts, very small quantities. But Nigeria has significant artisanal gold mining in Zamfara, Osun, and Niger states. Understanding bond types is the foundation for predicting and explaining chemical and physical properties, a core skill tested throughout WAEC chemistry. Key points: coordinate, dative, covalent bond. Both electrons come from the same donor atom, lone pair donor plus empty orbital acceptor. Examples: NH4+, H3O+, R2Cl6, CO. Metallic bonding, delocalized of electrons in a lattice of metal cations. Explains electrical and thermal conductivity, malleability, ductility, high melting points, luster. Comparison: ionic compounds, high MP, brittle, conduct when molten, simple molecular covalent, low MP, non-conductor, giant covalent, very high MP, non-conductor, except graphite, metallic, high MP, mostly, conductor, malleable. WAEC chemistry questions on bonding often ask: draw a dot and cross diagram showing a coordinate bond, explain metallic bonding and relate it to electrical conductivity, compare the properties of ionic, covalent, and metallic substances. Practice dot and cross diagrams for NH4+, H3O+, and CO to be examination ready.